In this video, we will give details of how the clock used on the Southwark Bridge Layout was made and operates. The first thing to do was to establish the requirements. For our purposes, we needed a clock to synchronise train movements, to give a sense of real operations, and to keep everyone paying attention. The clock needed to be displayed at 3 key locations along the layout, visible to train drivers, signallers, and to the fiddle yard operators. We wanted the clock to have a traditional feel, our model being based in 1912. So we based our design on the one at Waterloo, whilst at the same time showing a digital version for ease of use with operators in the 2020s. An unusual twist is that the digital clock operates in a 12-hour cycle, using AM and PM rather than as a 24-hour clock. This then ties in exactly with the timetable timings based on practice in 1912. We also added 1-second resolution to drive up precision of operations. The clock operator is normally one of the signallers on A box, so the control panel sits on the signal box shelf. The box serves two purposes: to provide a base for the control buttons and to house the Raspberry Pi computer, which is used to run the clock. The controls required to make the clock function are: run pause, 2 large buttons, green and red respectively, set current time for hours and minutes, plus and minus buttons, and speed. The clock speed can be fast, normal, slow, and slower, which roughly translates to 1.5, 1, 3/4 and half actual time. This allows for differing operator capabilities. To avoid confusion when running the 11 AM to 1 PM timetable, we have a second ordinary clock in the train room displaying pub time. Interestingly, operations usually speed up after a lunchtime visit to the pub. Clearly, these requirements could not be met with an off-the-shelf product, so we investigated various options to make it ourselves. Electromechanical devices were discounted, as the clock needed to be visible in 3 locations, all synchronised and controllable for speed from A-box. Whilst this was done on the real railway years ago, we felt this would be difficult to replicate and probably rather expensive. Instead, we chose to go for a digital approach, as this could be done quite cheaply with a small computer, a Raspberry Pi 2 Model B, costing about £30, and 3 identical monitors, about £65 each. The design of the display on the monitor had to be very easy to read at a glance, so we chose to make it very plain with a monochrome background image based on the clock face at Waterloo shown earlier. We couldn't resist adding the little flourish of makers' names for the members of the group that worked on the clock project: Mike Day, Chris Simpson and Ted Stevens. On top of the background we superimpose hour, minute and second hands orientated to the required position. The design for the hour and minute hands came from the original clock at Waterloo. The digital clock had to be readable at 3 or 4 meters, so the numerals are large and use a simple font. The image of the clock shown on the monitor is updated every 1 second of clock time, not actual time. To meet the requirement that the clock should show a resolution of 1 second meant that whatever we did in our program had to run in less than 2/3 of a second, to allow for the clock running in fast mode. A delay at the end of the program cycle brought the overall time up to the required interval depending on the speed of operation: fast, normal, slow or slower. The program code has 2 distinct parts. The first is the detection of the control buttons that may be being pressed by the A-box signaller. The second is the building of the next image of the clock for display on the monitor. Button press detection is achieved by connecting the buttons on the control box to various pins on the Raspberry Pi, and then reading each of the pins in turn at the beginning of each clock cycle to check if a button is pressed. If it is, then take the appropriate action. Experimentation and reading other people's observations on the internet, we came up with a solution which is reasonably reliable and eliminates issues such as contact bounce by testing if the button is held down for more than 6 out of 10 instances of repeated reading. Quite arbitrary, but seems to work. We had come across the concept of using a file containing a series of images to display pressure gauge settings in train simulators, but couldn't find an easy way to generate this type of file or code to display them using a Raspberry Pi. Also, the volume of data required to show a full 24 hours of clock in 1-second increments on a reasonably high resolution screen was expected to be rather large. Eventually, we came up with the idea of adding together different elements of the display to make up the whole image as the clock was running. The composite image is made up from a background, the hour hand, a minute hand, a second hand, and digital display numerals for hour, hour, minute, minute, second, second, and AM or PM, to give the final image ready for display. The advantage of using a monochrome display is that we could write the code to overlay each of the part images ourselves, giving us the ability to optimize how this works. The size of the final display is 900 by 1600, giving 1.44 million pixels. All of these would need to be processed during each overlay, and given that 13 overlays are needed to be performed for each frame build, we found, not surprisingly, that this couldn't be achieved in under 0.6 seconds on a Raspberry Pi. This problem was solved by reducing the tile sizes to a minimum, thus reducing processing effort when adding them together. The overlay process measures the offset of the images from top left. Each of the letter images was designed to be exactly the same size, to simplify the combination process. The file format chosen for the image was bitmap, because this was easy to read, gave best quality, and didn't require any uncompressing. The images were drawn in the MicroStation CAD system and then saved as bitmaps. We also found ways to reduce the data volume by use of symmetry. The clock hands move through angular increments. For the hour and minute hand, this is in 2-degree steps, requiring 45 images per quadrant. For the second hand, it is 6-degree steps, equates to 1 per second, requiring 15 steps per quadrant. This combination gives a reasonably smooth and graduated movement to the hour and minute hands, whilst the second hand has a distinct tick-like movement to it. You will notice that the images have only been made up for 1 quadrant of the clock. For the other 3 quadrants, there is code in the program to rotate the image to the required quadrant. So, for example, the same second-hand image is used for 1 second, 16 seconds, 31 seconds, and 46 seconds, simply rotated by 90, 180, or 270 degrees. The code for rotating the image achieves this by adjusting the order in which the pixels are overlain onto the assembled clock image. To rotate the image, the pixels are written in ascending or descending order for each axis depending on which quadrant the tile is to be applied to. Pixel positions are measured from top left and start from 0. The images for the background, hour, minute and second hand are then assembled into an analog clock face image with the time displayed on it. To do this, each pixel from each clock hand image is red. If it is black, then the pixel in the clock face image is set to black. If the clock hand pixel is white, then the pixel in the clock face image is unchanged. Thus, each hand is added to the clock. At this point, any temporary working images are destroyed to free up memory on the Raspberry Pi. The digital display is assembled in a similar manner. Each tile is added to the final picture. To assist the clock operator, 2 items of information are added to the display. If the clock has been paused, then a pause message is displayed on the top left corner. In the top right corner, there is a message showing the clock operating speed, fast, normal, slow, or slower. The assembled clock image is then displayed, and any temporary working images are destroyed to free up memory. A short delay is then inserted, the length of which is determined by the speed setting. Our original aim was to run this on a Raspberry Pi Zero on the left, but when we tested it we found that it simply couldn't run fast enough, so we opted to use the Raspberry Pi 2B instead. The computer was set up to run headless and to auto-start the clock program when booted. From an operator's perspective, all they have to do is turn on the computer, wait for it to boot, and auto-start the clock, then set the time using the control panel buttons. To display the image concurrently on 3 monitors, we added in a multi-channel display splitter box for HDMI signals. This is commonly available technology from any good hardware supplier. One mistake we made: we hadn't appreciated that standard issue monitors have a bias to the viewing angle, which is commonly orientated upwards for a monitor to be viewed in landscape. When turned to portrait, as we required for the clock display, this makes viewing from one side very good, but from the other side the display colours go distinctly yellow and it isn't always easy to see the display. It is quite easy to buy monitors which are designed for portrait and landscape use. We just didn't know it was an issue. Whilst it is quite a crude solution, it works and is reliable. We have run it for the last 2 years without any problems. All the files used to create the computer program for the clock and supporting images can be downloaded from here. These are provided on an as-is basis and no support can be provided. That concludes our presentation about the clock used on the Southwark Bridge layout. Thank you for listening and we hope you found it of interest.